Right, hello everyone and welcome to lecture 13 of computer architecture. Today we're going to be talking about floating point numbers. And specifically we're going to talk today about how we represent floating point numbers. Next lecture we'll talk about how to process floating point numbers in hardware. Last time we spoke about multiplication. We saw how to multiply numbers in hardware. And we're approaching the last part, bit of part one of the course. In fact, this week is the last week in which we will cover, look at part one. We still have 2 more lectures to go. We saw how we did multiplication kind of by hand, where we multiplied 2 numbers, and by multiplying these 2 numbers, we just got the multiplicand shifted by 1 every time, or it could be all 0, depending on the bits of the multiplier. And then we added all these numbers together, and our question was, how can we implement this procedure in hardware? And we looked at different hardware implementations to do this. Implementation, what we did is we considered the multiplication of 2 4-bit numbers to be equivalent to an addition of 4 8-bit numbers. And what we did is we initialized the product to 0, and then we just started adding these 8-bit numbers together until we got the final product. The product, of course, is going to be 8 bits. So we viewed the multiplication as an addition of 8-bit numbers, and this was the hardware that fulfilled this procedure. So we had an 8-bit multiplicand, and this multiplicand was shifted left by 1 every cycle. And we had an 8-bit product that was initialized to 0 and that we accumulated to every cycle. So here the product would be added to the ALU, will be added to the multiplicand by the ALU, and the result would be product. And then we used the bits of the multiplier here. So we used here the last bit of the multiplier, which was being shifted right every cycle, to select whether or not we wanted to write the result of the addition to the partial product or not. Obviously, if it was 0, we don't want to write, so this would be equivalent to adding 0, multiplying by 0 and adding. And if it was 1, then we write, because this would be equivalent to multiplying by 1 and adding. We then saw how we can improve on this this hardware multiplier by instead of viewing these as additions of 8-bit numbers, we observed that this number here on the left, these numbers here on the left, were all just a shifted version of the same 4-bit number. And that at any point in time in the addition, we were only interested in adding 4 out of the 8 bits. Because here only 4 bits were interesting and the other 8 bits were always 0, the other 4 bits were always 0, we knew that, for example, these 2 1s over here will always be added to 0. So there's no point in having an adder that adds them. We know that these ones will always be carried forward because they're added to 0. The only interesting addition that's taking place is for these 4-bit numbers, these 4 bits over here with these 4 bits over here. So what we this by using a 4-bit ALU instead of an 8-bit ALU, by keeping the multiplicand stationary, and by shifting the product instead of the multiplicand. By shifting the product and considering this top 4 bits of the product to be this logical window here, we were able to add the 4 bits that we cared about from the product to the 4 bits of the multiplicand in the right place value. And we also saw how since the number of bits that we don't need in the product register were the same as the number of bits that we needed in the multiplier register, we used the same register to store the product and the multiplier, and we shifted them by 1 every cycle, because every cycle we needed 1 more bit for the product and 1 less bit for the multiplier.
Professor?
Another technique for, does someone have a question?
Yeah, I don't want to interrupt you, but my question is like here. Here when we put an 4-bit LAU, this will lead to overflow, right?
Okay, so if we when we're multiplying 2 4-bit numbers, the largest number that they can have that can be created as an 8-bit number. So we don't have overflow in terms of the product down here. But what you're saying is true in the sense that when we add 2 4-bit numbers, we can have overflow. So the C out can be 1. But in this case, what we're doing is we're taking that C out as the 5th bit of the sum over here. So when we add two 4-bit numbers, we're actually taking a 5-bit result and shifting that into the 8-bit product. Okay.
So there is overflow, but we don't care. We are taking all the.
There is overflow. That
With
overflow
respect to the
is the
4-bit.
bit. There is overflow. We do care about the overflow. We're taking the C out bit, which is the overflow, and using that as the 5th bit over here. So you'll notice here we actually have 5 bits that are being produced. Okay.
Okay.
So this 5th bit over here is coming from the C out.
Okay. Thanks.
Okay. Yeah, you're welcome. That's a good question, actually. A third way of doing multiplication, and here we cared about speed. We said we wanted to finish the multiplication as fast as possible, even if that meant using more hardware. And unlike the previous two approaches where we used the same ALU and added the n numbers sequentially, over here what we did is we used different ALUs to add, for example, the first and the second number, and then at the same time add the third and the fourth number together, and then we have an ALU that adds these two partial products together to get the final product. Okay, and this was an example of how we could use more hardware in order for us to finish in less time. And we saw the trade-offs between the three designs. In the first design, we used if for an n-bit multiplier, we needed two n-bit ALUs, 5 n bits of register space, and we needed n cycles to complete. The second design improved on the first design by reducing hardware usage, but using the same amount of time. And the third design increased the amount of hardware that we used, but reduced the amount of time taken to do the multiplication. So that was what we covered last time. Any questions about material before we move on to today? Any questions? Okay, well then let's start talking about floating point representation. So if I'm going to review positional numeral systems very briefly. So if you remember from in a positional numeral system, what we said is that we combine symbols together by multiplying each digit by the base to the power of the digit's position and then adding the result. So for example, if we have 735 in base 10, we said that what this means is 7 times 10 to the power 2, because here the 7 is in position 2, 3 plus 3 times 10 to the power 1, because here 3 is in position 1, and then plus 5 times 10 to the power 0, because here 5 is in position 0. Okay. Similarly, binary worked the same way. If we had 101 base 2, what this meant is 1 times 2 to the power 2, because this 1 is in position 2, plus 0 times 2 to the power 1, because this 0 is in position 1, and plus 1 times 2 to the power 0, because this 1 is in position 0. So this is how we use the positional numeral system to represent integers. And what we would like to do is we would like to extend this to also be able to represent real numbers. Okay, so let's take a look at how to do that. So if we want to support real numbers, the way the decimal system does it is that we have a point, and then we have these digits to the right of the point, and they're multiplied by the base to the power of some negative number. Okay, so we consider their positions to be negative numbers, and we multiply them by the base to the power of those negative numbers. Let me show you what that means. So if I have 735.48 in base 10, what this means is that we have what we had before, 7 times 10 to the power 2 plus 3 times 10 to the power 1 plus 5 times 10 to the power 0. But what we also have is plus 4 times 10 to the power minus 1 plus 8 times 10 to the power of minus 2. So we have this point over here that distinguishes between whole numbers, integers, and then the fraction part of the real number. And here, when we have 0.48, we consider 4 to be in position minus 1 and 8 to be in position minus 2. And the way we get our final real number that's represented by this sequence of symbols over here is by multiplying 4 by 10 to the minus 1 and multiplying 8 by 10 to the minus 2. Okay? So this is how we supported real numbers in decimal. And just like with whole numbers, we can do the same thing for binary. So in binary, we can write 101.101, and what this means is what we had before: 1 times 10 to the power 2 plus 0 times 10 to the power 1 plus 1 times 10 to the power 0. And then after the point, we consider this 1 here in position -1, this 0 in position -2, this 1 in position -3. So what we have is plus 1 times 2 to the power -1 plus 0 times 2 to the power -2 plus 1 times 2 to the power -3. Okay, so this is, we can use the same strategy that we use to support real numbers in decimal to also support real numbers in binary. Okay, any questions about this? Okay, so let's see, we saw before how we can convert a decimal number into binary. So let's see how we can convert a decimal number that's an integer to binary. Let's see how we can convert a decimal number that contains a fraction or digits after the decimal also into binary. So if you remember, when we converted from decimal to binary, what we did is we successively divided by the number by 2 and extracted the remainder. So we started, for example, if we had 94 base 10 and we want to convert that to binary, what we did is we divided 94 by 2, we got 7 remainder 0, and then we divided 47 by 2, we got 23 remainder 1, then we took 23, we divided that by 2, we got 11 remainder 1, and we kept doing that, okay, and the answer was these remainders that we were getting over here, 1 0 1 1 1 1 0. So 94 in base 10 is these remainders over here, 1 0 1 1 1 1 0 in base 2. Now in decimal, if we want to convert for real numbers, if you want to convert a real number that's written in decimal to binary, this procedure is similar, but instead what we're going to do is we're going to multiply by 2 and extract the digit to the left of the point. So for example, if we have 0.78125 in base 10, and we want to convert this number into binary, the way we would do that is we would 0.78125, multiply that by 2, that gives us 1.5625, okay? We're gonna take this 1 aside, and then what next, we're going to take the remaining fraction over here, which is 0.5625. We're going to multiply that by 2. We're going to get 1.125. We take this one aside, then we take the remaining fraction, 0.125, we multiply that by 2, we get a 0. We take the 0 aside, we take 0.25, multiply that by 2, we get another 0, and then we take the 0.5, multiply that by 2, we get 1. So once we hit 1.0 over here, okay, our fraction is going to be 11001. So it's going to be these numbers over here to the left of the decimal, okay? So 0.78125 base 10 in binary, to convert that to binary, is going to be 0.11001, okay? And kind of intuitively, what this means is we're going to have 1 times 10 to the power times 2 to the power -1, so that's going to be 0.5, plus 1 times 2 to the power of -2, so that's 0.25, so 0.5 plus 0.25 is 0.75, and then you can verify that here 1 times 2 to the power of -5 gives us the final number that we're looking for, 0.03125, which if you add that to 0.75, you get this number over here, okay? So this is how we can convert the part after a decimal from the part after a decimal point from decimal to binary, okay? Any questions about converting from between decimal and binary for real numbers? Okay, so now that we've seen how to represent real numbers in binary, the question is, how do we actually represent real numbers in binary in the actual hardware? Okay, so we've seen before that, with whole numbers, we can represent an arbitrary binary number as a whole number, but we have a limited number of bits in hardware that we can use, and that gives us a limited number of integers that we can represent. Well, it's the same thing for real numbers. For real numbers, if we wanted to use a fixed number of bits to represent the real number in hardware, there are various considerations that we have to take, okay? So representing real numbers in hardware. How do I represent real numbers using a limited number of bits? One possibility is to use something called the fixed point representation. So what is the fixed point representation? The fixed point representation is I will say that I have a certain number of bits. If I have a 32-bit number, for example, I will consider a fixed number of bits to be the bits before the decimal and a fixed number of bits to be the bits after the decimal. So for example, if I have a 32-bit word, I can consider the first 16 bits, these are the bits before the decimal, and the remaining 16 bits, these are the bits after the decimal, okay? And that's why this representation is called fixed point, because you can think of the decimal point or just the point as being in a fixed position inside of our 32-bit word, okay? So this is one possible representation of real numbers. Now there are limitations to using the fixed point representation, which I will talk about. So the limitations of using fixed point representation is that they give you a very limited range. So for example, if I'm using if I'm using fixed point representation, I have a 32-bit number, and I say, okay, the first 16 bits before the decimal are going to be the first 16 bits are going to be the bits before the decimal, and the following 16 bits are going to be the after the decimal. Well, let's look at what happens in this case. In this case, the largest number I can represent, the smallest number I can represent is 2 to the power negative 16, and the largest number I can represent is 2 to the power 16 minus 2 to the power negative 16. Let me show you why. So here, if I'm using if I'm representing my real number as a 32-bit, using 32 bits, and I consider the 16 bits to the left, the first 16 bits to be the bits to the left of the decimal, and the remaining 16 bits to be bits to the right of the decimal, then the smallest number that I can represent is going to be 0, 0, 0, 0, 16 times, and then I have point, okay. So here, this is meant to be kind of not the decimal point. These points over here are meant to be just kind of like etc. And then here I'm going to have 0, 0, 0, etc. 16 times, and then I'm going to have a 1. Okay, so this is the smallest number that I can represent using a fixed point representation. And what does this number over here mean? Well, these are all 0, 0, 0, 0, and then I have 0 to the times 2 to the power minus 1 plus 0 to the 2 to the power minus 2, all the way to position negative 16. So here, the smallest number I can represent is 1 times 2 to the power negative 16. So this is the smallest number I can represent. So I can represent using fixed point is going to be when I have all ones. Okay, so it's going to be 1, 1, 1, 16 times, and then point, and then 1, 1, 1 again 16 times. Okay, so here, what is this number equal to? Well, this number is if you add 1 to this number, if you add if you add 0.00001 to this number, you're going to get 2 to the power 16 because you're going to have a 1 in position 16 and 0 everywhere else. So you can think of this number that's all ones as 2 to the power 16 minus 2 to the power negative 16. Okay. Now this is the smallest number that we can represent, and this is the largest number that we can represent. Okay, and what are these numbers equal to? What are these numbers equal to in decimal? Well, 2 to the power negative 16 in decimal is 1.525878 times 10 to the power minus 5. And 2 to the power 16 minus 2 to the power negative 16 in decimal is 6.553, this number over here, times 10 to the power 4. Okay? Now, as you can see, this range that we can get by using the fixed point representation is very limited, right? 10 to the power minus 5 is small, but it's not that small, right? And 10 to the something times 10 to the power minus 4 is large, but it's not that large, right? This, the largest thing I can represent here is something that's in the thousands, okay? And if you compare this to, and just to show you the fact that this is not that small, this is not that large, if you compare it to typical numbers that we like to store and operate on, the gravitational constant, for example, is 6.6743 times 10 to the power minus 11. So when the smallest number that we can represent has a magnitude of something times 10 to the power minus 5, it means we cannot even represent the gravitational constant. So if I have some physics computation that I want to do in my system, right? If I use fixed point, I won't be able to represent the gravitational constant, which is a very important number. Another number is Avogadro's number. So Avogadro's number is 6.022, etc., times 10 to the power 23. But if the largest number I can represent is times 10 to the power 4, that means I can't even represent Avogadro's number using this representation. So if I'm writing a program that needs to do some chemistry computations, I won't be able to even use Avogadro's number if I'm using the fixed point representation. Okay, so this is the limitation of fixed point. The nice thing about fixed point is that it's easy, right? When you consider the fixed point to be to just have your bits, but you have some imaginary point in the middle of these bits, then you can treat them just like integers, but you always remember that there's this point inside of it. But the drawback of fixed point is this limitation over here, that we cannot represent numbers that are very, very small and very large, like we usually care about when in kind of the real world. Okay. So the question is, can we do something better than this? Can we, instead of using fixed point, use some other representation that gives us a wider range, be able to use the same 32 bits, but represent numbers that are larger than this number over here and that are smaller than this number over here? And the answer is we can. This is, and to kind of motivate for that, I want to introduce the notion of normalized numbers. Okay, so in decimal, we have something called scientific notation, and scientific notation is convenient for representing numbers that have a very wide range. So for example, if I have a number like 920 million, okay, I have all these zeros in my number, and these zeros are kind of, they're important because they're important for the value of the number, but they're not that important to write, right? And if I have billions and trillions, I start having all these zeros that I need to write down when writing a decimal number. But they're important in terms of the value of the number, but they're not that important for kind of to get a good idea of what the number is. So it's more convenient for me to use something called scientific notation, where rather than writing 9.2 and then all these zeros, I simply write 9.2 times 10 to the power 8. So you can see that writing 9.2 times 10 to the power 8 is much shorter than writing all these numbers over here. Over here, the number of digits that I need to write, I have 9 digits that I need to write to represent this number. Whereas here I only have, 9 and 2 and 8 that I need to write. Of course, there's the 10, but that's redundant. But the important digits that I need to write using scientific notation are just 3 digits. Whereas if I wanted to represent a number like this, the important numbers I need to write are 9 digits. Okay. Similarly, if I have a very small number like 0.00000043, again, I'm writing down all these digits, but really the important digits that I care about are the 4 and the 3, and then some number that gives me an idea of the magnitude of the order of magnitude. So I just write 4.3 times 10 to the negative 7. So here it was, the only important digits were 4, 3, and negative 7. Whereas without scientific notation, I have to write down all these digits. Okay. So scientific notation is useful for writing down numbers in decimal or representing decimal numbers more concisely. And the nice thing is we don't have to write down all these unnecessary zeros. We only need to represent the significand and the exponent. So these numbers over here are the significand, called the significand. And then when we write times 10 to the power of something, the power of 10 is called the exponent. Okay. So to represent a number in scientific notation, I only need to represent the significand and the exponent. So a number in scientific notation is normalized. So the same number can be written different ways in scientific notation. It's considered normalized when we have exactly one non-zero digit before the point. Okay, so for example, 9.2 times 10 to the power 8 is normalized, okay, I could have also written this number up here as 92 times 10 to the power 9, or I could have written it as 0.92 times 10 to the power 7, right? So these three are all valid scientific notation, and all three of these numbers are more concise than writing 920 million in this way. However, these two down here are not normalized. Only this one up here is normalized. So what we mean by normalized is we only have one digit before the point, okay? So what we're going to do is we're going to use this notion of scientific notation in order for us to also represent binary numbers more concisely, and what that also means is more compactly in hardware. And let's see how to do that. So the point representation for binary real numbers uses this idea of scientific notation normalization to represent real numbers with a wide range in hardware. For example, rather than writing 10101000 and have all these zeros, we can simply write 1.0101 times 2 to the power 13. And now, if we want to store this in hardware, all we need to store is the significand and the exponent. So all we need to store is these here, these bits over here for the significand, and then something to tell us that the exponent is 13. Similarly, if we have 0.00000 and then we have 101 over here, we can simply represent this as 1.011 times 2 to the power -9, and now we just need bits to store the significand over here and the exponent over here. Okay, and that's what we're going to do. So we don't need to store all the bits in the number. All these zeros to the right or all these zeros to the left are unnecessary to store. We just need the bits to store the significand and the exponent, and that enables us to use our 32 bits or our 64 bits that we want to represent the number in more efficiently. Okay. So in summary, floating point is a representation for non-integer numbers, so for real numbers, and they can be used to represent very small numbers and very large numbers. And they're like scientific notation. So I already spoke about scientific notation and showed you how floating point is similar to scientific notation. And we have we're gonna use normalization to represent our floating point numbers, and we're not gonna use these not normalized numbers. And the way we're going to do it is we're going to represent our floating point numbers as, in general, plus or minus 1.xxxxx in base 2 times 2 to the power y in base 2. So rather than having a fixed point representation, what we're going to do is we're going to have a floating point representation where we only need to store these x's over here and these y's over here. And notice an important point is that we don't need to store this 1, right? So a binary in decimal, right, the number to the left of the point can be a 1, it can be 2, can be 3, can be 4. But in binary, the number to the left of the point is always going to be a 1. Okay, it's always going to be a 1. So there's no point in storing it. We can save a bit by always kind of implying that there's a 1 over here and only storing these bits to the right of the point. Okay, so that helps us save a bit. Okay, so we just want to store these x's and just want to store these y's. This is how you're probably familiar with float and double in C or C++. So this is the representation that's used to store float and double types inside of a computer. We use floating point representation where we just store the bits of the significand and the bits of the exponent. Okay. Okay, so let's see how this is done. There's a floating point standard. And the reason there's a standard is because, the standard is defined by IEEE, which the Institute for Electrical and Electronics Engineers. This is an international organization that helps kind of organize electrical and electronics engineers. And IEEE has defined a standard for representing floating point numbers. The reason this standard was developed is because once people started using computers and they started representing real numbers, many different people were representing real numbers in different ways. And this created a problem for people who write in scientific code, because if you wrote code that represented real numbers in one way and I wrote code that represented real numbers in a different way, it's hard for our codes to interoperate. So IEEE did is they came and they defined a standard for representing floating point numbers. And the standard is now almost universally adopted. And there's two representations in the standard. There's single precision and there is double precision. And we're going to talk about those representations today. So let's look at what the floating point representation looks like. We're going to have 32 bits for single precision or 64 bits for double precision. In both cases, we're going to have one bit, which is going to be the sign bit. This bit is going to tell us if the number is positive or negative. So we're not going to be using 2's complement here. We're always going to be representing unsigned numbers and using this bit to tell us if the number is positive or negative. We're going to have a number of bits for the exponent for single precision, and then a number of bits for the fraction. The fraction here refers to the bits after the decimal point. Okay. The exponent is going to be 8 bits for single precision and 11 bits for double precision. And the fraction is going to be 23 bits for single precision and 52 bits for double precision. Okay. So how do we interpret these bits over here? Well, this equation kind of tells us what these bits mean. We're going to have -1 times time to the power of s. So here, if s was 0, -1 to the 0 is 1. So we're going to have a positive number. If s was 1, the -1 to the s is -1. So we're going to have a negative number. And then we're going to have 1 plus the fraction, or you can think of this as 1 point and then the bits of the fraction. Okay, so the significand is going to be 1 point and then the bits of the fraction. And then you can think of the exponent as here being the exponent minus a bias. So here, the bits that we're going to store here, these are going to be an unsigned number, but we want to be able to represent positive and negative exponents. So we're going to have a notion of a bias, and we're always going to subtract this bias from an exponent. And all this will be clear when I do an example shortly. So in summary, we're going to have s as the sign bit. If it's 0, that means the number is positive, or non-negative. If it's 1, that means the number is negative. We're going to have a normalized significand. So the significand is always going to be between 1.0 and 2.0. So it's going to be 1 point something, and that something is going to be represented by this fraction bit over here. And again, we don't need to store this 1 to the left of the point. That one is always implied. And then we have an exponent. And this exponent is going to be a positive number, but we're going to subtract a bias from it. Okay. And for single precision, the bias is 127, and for double precision, the bias is 1023. Okay, so for example, if we wanted our exponent to be 1, we're going to store 128 inside of these 8 bits, and that way our exponent is going to be, or our exponent here is 128, so our actual exponent is going to be 128 minus the bias, which is 127. Sorry, it's going to be 2 to the power 1. Okay, if in single precision we wanted to store, we wanted something times 2 to the power -1, then we would store 126 in this exponent over here, and that way our actual exponent will be 126 minus the bias, which is 127, and that will give us 2 to the power -1. Okay, let's do some examples. I know I've thrown a lot at you, so let's do some examples to make this clearer. As an example, if we had this number over here, if I gave you this sequence of bits, and these are 32 bits if we include the bits that I'm skipping over here, and I told you this is a floating point number, what number does this floating point value represent? Well, you're going to take the first bit and you're going to count that first bit as your sign bit. You're going to take these 8 bits over here and you're going to count those 8 bits as your exponent. Then you're going to take the remaining bits and you're going to count these remaining bits as your fraction. Okay, so here our sign bit's going to be 1. Our fraction bits are going to be these bits over here, the last 23 bits. And our exponent is going to be these bits over here. But remember that the exponent is biased. Okay, so here these bits over here have the value 129, but the actual exponent is going to be 129 minus the bias, which is 127. So this number over here is going to be -1 times -1 to the power of the sign bit, which is 1. So it's going to be a negative number, times 1 point, the fraction bits over here. So here the fraction bits are 0, 1, and then a bunch of zeros. So it's going to be 1.01 times the exponent times 2 to the power of the exponent minus the bias. So it's going to be 129 minus 127. So here this is going to be -1 times 1.25 times 2 to the power 2. Okay, and this value comes out to be -5. Okay, this sequence of bits over here represents -5 as a real number, or -5.0. Okay? Any questions? Any questions so far? Am I going too fast? Am I going too slow? Or is everyone following? So someone's asking for an example, it will be positive. Yeah, so if it were positive, then here this sign bit will just be 0, and then will have -1 to the power of 0, which will just be 1, so that will give you positive 5.0. So the only difference between a positive and negative number is that this sign bit over here will change. Everything else will be the same. Again, we're not using 2's complement here. We're always going to represent the fraction as unsigned values. And the way we get negative numbers is using the sign bit, and the way we get negative exponent is by subtracting a bias. Okay. Other questions?
Sir, what if we have only one, like, مش 32 bits? If we have one bit, like number 1, how do we represent it?
So usually I mean, usually 1 bit is not going to be enough for you to represent a floating point number, right? You need a bit for the sign, some number of bits for the exponent, some number of bits for the fraction. If you want to represent the value 1 as a 32-bit floating point number, well, you're simply going to have your sign is going to be 0. Your significand is going to be 1.000, so you're just going to have a bunch of zeros in your fraction bits, and then you're going to pick your exponent here. You're going to set this to 128, so that 120. Sorry, you're going to set this to 127, so that here the exponent will be 127 minus 127. So it'll be 1 times 2 to the power 0, which is 1. Okay. So that's how you would represent 1 in floating point.
Okay, thanks.
Yeah, you're welcome. Okay, so now let's look at, so we've seen how we can take a sequence of sequence of bits, and if I tell you these bits represent a floating point number, you can find the corresponding floating point number they represent. Now let's do the opposite. Say we have a -0.75, and we want to represent this as a floating point number. Okay, well, what do we need to do? Well, we need to extract 3 parts. Okay, we want the sign, we want the fraction bits, and we want the exponent. But of course, this is a decimal number, so first we should convert to binary. So we convert this to binary. -5 is going to be -0.11 in binary, in base 2, right? Because 0.75 is basically 0.5 plus 0.25, which is 2 to the power minus 1 plus 2 to the power minus 2. So that's going to be -0.11 in base 2. And -0.11 in base 2, well, that's going to be -1 to the power of 1. So our sign bit is 1. And then if we normalize 0.11, we're going to get 1.1 times 2 to the power minus 1. So our fraction bits are just this 1 over here. And our exponent is -1. Okay. So our sign bit is 1 because the number is negative. Our fraction bits are going to be 1 and then a bunch of zeros because here the number we have to the right of the normalized value is just a 1. And then our exponent, well, that depends on the bias. Our exponent is going to be -1 plus the bias. Okay. So if we were using single precision, our bias is 127. So our exponent is going to be 126, which is this number over here in binary. And if we're using double precision, our bias is 1023, the number we store is going to be -1 plus 1023, which is going to be this value here in binary. And this way, if we wanted to represent -0.75 as a floating point number, the single percentage representation will look like this. We have 1 here, which is the sign bit. We have these 8 bits, which are the exponent bit, and then we have 1 and a bunch of zeros, which are the fraction bits. In other words, the bits to the right of the point. And if we want to represent this as double precision, we would have 1 here, which is the sign bit, and then these 11 bits are going to be the exponent bit, and then this last bit over, these last set of bits over here are going to be the these significant bits. So another, again, it's going to be 1 and a bunch of zeros. Okay. Any questions about how we convert a decimal number to single precision and double precision floating point representation? So someone's asking if this is enough to represent big numbers, and I'm going to talk about that immediately. Okay, so that's my next point. We're going to see what we can represent using this approach. But before that, any questions about how do I do the how you do the conversion? Okay. All right. So then let me answer your question about if this is enough. So there's two parts to this question: precision and range. Okay. So there's two parts of when I ask the question, what numbers can I represent using this representation? That question has two parts: precision and range. So by precision, what we mean is the number of significant digits that can be represented. Okay. How many digits can we represent? Okay, and the number of significant digits is impacted by the size of the fraction. Part of the question is the range. In other words, what is the scope of number that I can represent? How large and how small is the magnitude of the numbers that I can represent? Okay, and this is impacted by the size of the exponent. Okay, so there's two parts. What are the exponents that I can represent? That gives me the range, the largest numbers and the smallest numbers. And the other part is how many significant digits can I represent? Okay. So let's talk about first. So for precision, for floating point precision, and with single precision, we have 23 fraction bits. Okay. So I can have 1 point and then 23 bits. And these 23 bits, loosely speaking, so 23, the number of decimal digits that we can represent with 23 bits is almost 6 decimal digits. Okay, so here the way we get that is by multiplying by log base 10 of 2. Okay, which is 0.3. So 23 binary digits is equivalent, is enough to represent around 6 decimal digits. Okay, so to answer your question, is it enough to represent numbers like the number that was given? Well, the number that was given has more than 6 decimal digits. So if I want to represent this number in floating point, I would actually have to round it so that I would have around 6 decimal digits of precision, and then I can represent it. Okay. If I have double precision, with double precision, I have 52 fraction bits. So 52 times 0.3, right? Because every decimal digit, so every binary digit is around 0.3 decimal digits. So if I multiply 52 by 0.3, I can represent with double precision around 16 decimal digits of precision. Okay. So in this case, I can represent the number that was provided without rounding it. Okay. So precision here deals with the number of digits that we can represent. Now the question is range, right? And before we were more concerned about range. By the way, precision is very important. There are many applications, in scientific computations where people do actually need this many digits of precision, okay, in their computations. All right. But let's look at range. Range is kind of cool. What is the range of numbers that we can represent in each case? So here, I just want to point out that the exponents, all zeros and all ones, are reserved. Okay, we'll see later what we're going to use these exponents for. But for now, we are going to treat the exponents 0, 0, 0, 0, and 1, 1, 1 as reserved. We're not going to touch those. So if you want to reason about what is the smallest value that we can represent using floating point representation, so the smallest exponent we can have, here I'm going to look at single precision only. The smallest exponent that we can have is 0, 0, 0, 0, 0, 0, 0, 1. Okay. And the actual exponent for that is 1 minus 127, which is the bias, so negative 126. So the smallest exponent that I can have is negative 126. The smallest fraction that I can have is all zeros, basically. So the significand in this case is going to be 1.000000. So the smallest value that I can represent is plus or minus 1. So the smallest significand I can have is 1 times 2 to the power of negative 126. Okay, and this is equivalent to plus or minus 1.2 times 10 to the power negative 38 in decimal. Okay, so this is a big improvement over what we had before. So if you remember, in fixed point, the smallest number I could have was 2 to the power negative 16. Now the smallest number that I can have is 2 to the power negative 126. Okay, so I can represent the gravitational constant using this floating point representation. We will actually have even smaller numbers when we look at denormalized numbers, but I will talk about those later. For now, the smallest normalized number that we can have in single precision is 2 to the power negative 126, which is equivalent to 1.2 times 10 to the power negative 38. And by the way, by smallest here, I mean the smallest in magnitude. So I'm ignoring the negative. I don't mean the smallest and kind of including the most negative number. What about the largest value that I can represent? Well, the largest value that I can represent, the largest exponent that I can have, remember all ones is reserved, so the largest exponent that I can have is all ones and then a 0 at the end. So this value is equivalent to 254. So the actual exponent is going to be 254 minus the bias, which is going to be 127. So the largest exponent that I can have is 127. The largest fraction that I can have is all ones. So the significand for this is going to be 1.1111111111. That 1.111111 as almost being equal to 2.0. It's not exactly 2.0. It's 2.0 minus a very small number. Okay, so but it's almost 2.0. So here the smallest significand I can have is 2.0. The smallest exponent I have is 127. So the smallest value I can have is 2 times 2 to the power of 127, and this is equivalent to plus or minus 3.4 times 10 to the power 38. So this is a very big number, and this is enough for me to represent Avogadro's number. Okay? Any questions about how I found these ranges?
Sir, you mean the largest value, right?
Yeah. Oh, yes. Sorry. Okay. Yeah, there's a mistake in the slide here. I mean largest exponent, largest fraction, largest value. So I'll calculate better.
And is it 2.0 minus 0.00000 15 zeros 1?
Right. It's actually going to be 2.0 minus 0.0022 times and then 1. Remember the fraction bits are 23 bits.
Oh, yeah.
Right. So it's going to be minus 22 zeros and a 1. Okay.
Oh, okay.
So that's 2 to the power minus 23. Okay, which is a very small number.
Okay. Thanks.
Okay. Yeah, you're welcome. Any other questions? All right. Well, if there are no questions, I will stop here. And next time, I will continue talking a little bit about floating point representation. In particular, we're gonna here we're gonna look at double precision range. We didn't. So double precision is the same thing. The smallest value is going to be 1, but here the bias is different. So with double precision, the smallest number we can represent is 2.2 times 10 to the power of negative 308. And you know, it's unlikely that you will ever need to represent a number smaller than this. And then the largest value is going to be this is the largest exponent, which is going to be 1023, and the largest significand is 2. Again, there's a typo here. This should say largest. So the largest number you can represent is 1.8 times 10 to the power 308. And again, it's unlikely you'll ever need a number that's larger than this. Okay. So with that, that's all I have for today. Next time we will look more at floating point representations, and in particular, we're going to look at how to represent 0, because we still don't have a way to represent 0, and how to represent even smaller numbers or numbers that are not valid. Okay, that's all for today, and I will see you next time. Bye, everyone.